Good morning, students. In this lecture, we will study and discuss about basic circuit laws, about Ohm's law, Kirchhoff's current law, and Kirchhoff's voltage law, and how to determine equivalent resistance in a series circuit and in a parallel circuit, and we'll have examples. Ohm's law. The current flowing in a conductor is directly proportional to the applied voltage and inversely proportional to its resistance. That means if I have a circuit element, for example a resistor, then the voltage across the resistor is the current passing through the resistor times the resistance, or the current is equal to the voltage over the resistance, or the resistance equals voltage over current. Kirchhoff's current law. Kirchhoff's current law says the algebraic sum of all currents flowing into a junction is equal to 0. Junction means a connection point between circuit elements. For example, here I have this element, and this element. They are connected at point A. So point A is the junction point or the connection point. The total current entering the junction is equal to 0. Here we need to consider the current directions when we do the total current summation. If we assume the current entering as positive, then we should say the current leaving negative. Or if you assume the current leaving as positive, then the current entering should be negative, and vice versa. So, for example, if the total current entering junction A is equal to 0. In this example, the current entering is considered as positive. I1 is positive, that means I2 is negative, and I3 is negative. So I1 minus I2 minus I3 is equal to 0. Now I1 is known, I3 is known, therefore I2 is equal to I1 minus I3, which is 10 minus 3, 7 ampere. This is very important law, Kirchhoff's current law. Kirchhoff's voltage law. The Kirchhoff's voltage law says the algebraic sum of the total voltage in a closed loop is equal to 0. Here again, when we do the summation, we need to consider the signs. For example, when we are going across the loop, if we go from negative to positive, if we assume as positive, then from positive to negative, it will be positive. Or if we assume from positive to negative as positive, then from negative to positive should be negative. So we need to be careful about the signs when we do the summation across the loop. Now, in this case, we're going in this direction, which is clockwise. So from negative to positive is E is positive, and here across this element, this terminal is positive, so therefore we are going from positive to negative. It will be minus V1, and then for the second one, minus V2 is equal to 0. So E is known 12 volt, V2 is 7 volt. Therefore, how we find V1? V1 is E minus V2, 12 minus 7, 5 volt. Power dissipated in a resistor. The power dissipated across in a resistor is equal to the voltage across the resistor times the current passing through the resistor. P is equal to V times A. However, from Ohm's law, we know that V equals to I times R. So when we substitute for V, we get P is equal to I squared times R. Or if we substitute for I equals to V over R, we get for power P equals to V square over R. So these are the different alternatives that we can be able to calculate the power dissipated by the resistor. Series circuit, how we determine the total resistance of a series circuit and a parallel circuit. Here is the derivation for the equivalent resistance for a series circuit. Here I have three elements, R1, R2 and R3. And that is the voltage source. Note that in a series circuit, the same current flows inside the circuit. Therefore, I1, I2 is equal to I3. But the total voltage is V1 plus V2 plus V3. Using Kirchhoff's voltage law, we can find that the total voltage Vs, the source voltage, equals to V1 plus V2 plus V3. But V1 is I1 times R1, V2 is I2 times R2, and V3 is I3 times R3. Therefore, because I total, the total current, is the same as I1 is equal to I2, I3, then I will cancel. We find the total resistance for the series circuit is R1 plus R2 plus R3. So if we connect more elements, always for the series circuit, the total resistance is the sum of the resistance of each element. So we have, for example, here a series circuit having 1 ohm and 2 ohm. What is the total resistance? And 3 ohm. The total resistance is 1 plus 2 plus 3, 6 ohm. What is the total current or the current in the series circuit? The total current is the total voltage, which is 12 volt divided by the total resistance 6 ohm, and it will be 2 ampere. What is the current through each element? The current through each element is 2 ampere. Why? Because it is a series circuit and the same current flows through all elements. What is the voltage drop across each element? Very easy, because we know the resistance and we know the current from Ohm's law. The voltage across the 1 ohm resistor will be 2 ampere times 1 ohm, 2 volt. The voltage across the 3 ohm resistor is 2 ampere times 3 ohm, 6 volt. The voltage across the 2 ohm resistor, 2 ohm times 2 ampere, which is equal to 4 volt. If we add all this, we will have the total voltage, which is equal to 12 volt. Parallel circuit. In a parallel circuit, the total current, for example, I have here 3 branches, branch 1, branch 2, branch 3. The total current is I1 plus I2 plus I3. How to determine the equivalent resistance of a parallel circuit? This is a parallel circuit. In the parallel circuit, the voltage across each element is the same as the source voltage here, V. So V, the source voltage is V1 is equal to V2 is equal to V3. The total current from KCL, if we consider this junction, the total current is I1 plus I2 plus I3. Now, the total current is the total voltage divided by the total resistance, which is equal to I1 is V1 over R1, I2 V2 over R2, I3 V3 over R3. Therefore, 1 over R total, or for the parallel circuit, or the equivalent resistance, is 1 over R1 plus 1 over R2 plus 1 over R3. If we have more parallel branches, the total resistance is the reciprocal of the total resistance, 1 over R total, is equal to 1 over R1 plus 1 over R2 plus 1 over R3 plus etc. Now let's do this example. In this example, let's find the total resistance. I have 3 branches, 1 5 ohm, 7 ohm and 9 ohm. The total resistance 1 over R total resistance are parallel. This means are parallel. The equivalent resistance for the parallel circuit is equal to 1 over 5 plus 1 over 7 plus 1 over 9. So 1 over R parallel is equal to 0.4. So to get R parallel, we should make the reciprocal of 0.454, which is equal to 2.2 ohm. What is the total current? From Ohm's law, very easy. The total voltage equals to the total resistance times the total current. Therefore, the total voltage is 8. The total current equals to the total voltage divided by the total resistance, which is 8 divided by 2.2, which is equal to 3.64 ampere. What is the voltage across each resistor? Because it's a parallel circuit, the voltage is 8 volt. What is the current through each element? The current through each element is the voltage across each element divided by the current passing the resistance of each element. For example, the current through the 5 ohm resistor is 8 divided by 5, 1.6 ampere. The current through the 7 ohm resistor is 8 divided by 7, 1.14 ampere. The current through the 9 ohm resistor is 8 divided by 9, 0.9 ampere. If we add all these currents, we'll get the total current, which is 3.64 ampere. Now, let's have a little bit more advanced circuit, and let's try to find the total current and the total resistance. In this circuit, I have series and parallel combination. The 100 ohm is in parallel with the 50 ohm. So the total resistance of the circuit is the 100 ohm in parallel with 50, and it will be in series with 80. So first we calculate the parallel combination resistance of the 100 and the 50. It will be 100 times 50 divided by 100 plus 50, which is equal to around 33.33. And when we add it with 80, we will get the total resistance 113.33. And since the total voltage is given 120 volt, the total current passing through the circuit is 120 divided by 113.3, which is equal to 1.06 ampere. Now, how we find the voltage across the 80 ohm, the 80 ohm resistor, and across the 100 ohm resistor, across the 50 ohm resistor? The voltage across the 80 ohm resistor is the total current times the 80 ohm. The total current is 1.06 times 80, which is equal to 84.8 volt. Then the total voltage is the voltage across the 80 plus the voltage across the resistance R2 or the resistance R3, because they are in parallel, they have the same voltage. Therefore, 120, the total voltage is V1 plus the voltage across resistor 2 or across the resistor 3. And from this relation, we get the voltage across resistor 2 or resistor 3 is 35.2 volt. Now, what is the current passing through R2 and R3? From Ohm's law, the current passing through the 100 ohm resistor is the voltage, which is 35.2 divided by the resistance 100 ohm, which is 0.352 ampere. The current through R3 is the voltage 35.2 divided by the resistance 50 ohm, 0.704 ampere. And if we add these two, we get the total current 1.06 ampere. Now, in the next circuit, let's determine the total current and the total equivalent resistance. Now, in this circuit, again, I have series parallel combination. Here I have R2 in parallel with R3. R2 in parallel with R3 is equal to, how we determine 1 over R total for R2 and R3 is 1 over R2 plus 1 over R3, which is equal to, from this we get the R2 in parallel with R3 will give me 4 over 3 ohm. Now the total resistance of the circuit is R1 plus the parallel combination of R2 and R3 plus R4, which is equal to 1 plus 4 over 3 plus 3, 16 over 3, which is 5.33. The total current is the total voltage divided by the total resistance. The total voltage is 16 divided by 5.3, which is equal to 3 ampere. Now let's let's have another example, and let's determine the current Ix, Iy, and Iz for this circuit. For this circuit, we have 14 volt source and 12 volt source. So to solve this problem, we need to use both Kirchhoff's current law and Kirchhoff's voltage law. For Kirchhoff's current law, we have the relation between Ix, Iy, and Iz. For example, here the current entering is Ix, and the Iz, and the current leaving is Iy. So therefore, Ix plus Iz is equal to Iy. The total current entering is equal to the total current leaving the junction. So we have one relation between Ix, Iy, and Iz. Another relationship is from this loop, from the left loop and the right loop. From the left loop here, if we say, for example, from negative to positive is positive, and from positive to negative, negative. If we go to across this loop, 14, okay, the total voltage across this loop is equal to 0. 14 plus 14 minus 4ix minus 2iy is equal to 0. And for this loop, if we do the same loop, the same for this loop, 12 minus 6iz plus minus 2iy is equal to 0. So here, from the Kirchhoff's current law, we have Iy is equal to Ix plus Iz. From Kirchhoff's voltage law of the left loop, we have minus 2Iy plus 14 minus 4Ix is equal to 0. And from the right loop, minus 2Iy plus 12 minus 6Iz is equal to 0. Now, if we see this equation, the third equation, I have Iy and Iz, and in the second equation I have Iy and Ix. So if we substitute for Ix in terms of Iy and Iz, then I will have two equations with two unknowns, which are Iy and Iz. So here that's what I did. So Ix is Iy minus Iz. So I substitute in this equation minus 2Iy plus 14 minus 4, okay, Ix, I substitute for Ix. What is Ix? Iy minus Iz is equal to 0. So if we simplify this, we have minus 6Iy plus 14 plus 4Iz is equal to 0. So I have one equation in terms of Iy and Iz. One equation, minus 6Iy plus 4Iz is equal to minus 14. And another equation from the right loop, minus 2Iy minus 6Iz is equal to minus 12. So I have two equations with two unknowns. This is simultaneous equation we can solve by eliminating one of the variables and solving for the other variable. Here, what I did, I tried to eliminate Iy. So to eliminate Iy, I multiplied by minus 3. If we multiply by minus 3 the second equation, I will have 6Iy plus 18Iz is equal to 36. Then if you add these two equations, minus 6Iy plus 6Iy 0, 4Iz plus 18Iz, 22Iz, minus 14 plus 36, 22, 22Iz is equal to 22, Iz is 1 ampere. Now we find Iz, therefore from the third relation, if we find Iz, we can find Iy. So substitute for Iz 1 ampere, we have this. So minus 2Iy is equal to 6 minus 12 minus 6. So Iy is 3 ampere. Now we find Iy is 3 ampere. Therefore, from this relation, Iy is equal to Ix plus Iz. then Ix is equal to Iy minus Iz 3 minus 1, 2 ampere. Alright, and this we have a voltage divider circuit. As you see, this is a voltage divider circuit. The voltage between this point and this point is V1 minus V2. So V1 minus V2 is divided between R1 and for R1 and R2. So the voltage across R2 is V1 minus V2 times R2 over R1 plus R2. So the total voltage V at point A is the voltage V2 plus the voltage across the resistor 2, which is V at point A is V2 plus V1 minus V2 times R2 over R1 plus R2. If V2, yes, this is how this one shows how I derived the voltage divider equation using two loops. For example, here I have loop K and loop J. So in this loop, I have minus V1 plus, because the same current flows, I times R1 plus R2 plus V2 is equal to 0. Therefore, I is equal to V1 minus V2 over R1 plus R2. I means the current flowing through R1 and R2. And in the loop J, I have minus V2 minus I times R2 plus the voltage at point A, VA is equal to 0. So the voltage at point A is V2 plus I times R2. Therefore, the voltage at point A is V2, I times R2. R2 is V1 minus V2 over R1 plus R2, which will give you this relationship. Now, if V2 is 0, simply the voltage V at point A will become V1 minus V2 times R2 over R1 plus R2. This example shows V1 is 10 volt, V2 is 0 volt. Therefore, the voltage at point A is V2 is 0, V1 minus V2 is 10 volt, 10 times R2 over R1 plus R2, 10 times 300 over 500, which is equal to 6 volt. And we have another example here. V2 is 3 volt. It's a matter of substitution now. And the voltage at point A is V2 again plus V1 minus V2 times R2 over R1 plus R2. Substitute the numbers and we have 7 volt here. Sinusoidal quantities. When you talk about sinusoidal quantities, we have voltages and currents which vary sinusoidal sine and cosine. The waves are sine and the voltage and the signal are sine form and cosine form, that means. So when we talk about sinusoidal quantities, we need, the first thing we need to know is the period or the fundamental period. What is the fundamental period? The fundamental period is the length of time between two similar identical points in successive cycles. So we start at one point, we trace until we come back to the same point. For example, here we start at 0, we go up, positive, increase and then decrease, and we go to negative, come back to 0, and we repeat the same. Therefore, this is the period T, one full cycle. Go up, go down, and back, and then it will repeat itself. A quarter of a period, as the quarter of the period, we have maximum point, and at the half period, we have the 0 point, and at 3 times T over 4, we have minus Vp point. Vp is called the amplitude, the peak voltage. Omega is the frequency in radians. It's given by 2 pi times f. F is the frequency in hertz, and F is equal to 1 over T, where T is the unit for T is second, the unit for the fundamental period. So the unit for frequency is cycles per second, or it is hertz. Now, if we have this example, for example, from this diagram, we can be able to identify the peak voltage, the period, the frequency, and in hertz, and the frequency in radians. Here, for example, we start how to find the period. We start from 0, go up to the peak value, which is 10, and come back to 0, go to the negative peak minus 10, and come back to 0, and then this will repeat itself. Same thing will repeat itself. So from this diagram, the period is 0.02 second. And that means the frequency is 1 over the period, 50 hertz, 1 over 0.02, 50 hertz. And omega, the frequency in radian per second, is 2 pi f, which is equal to 314.1593 radians per second. This is practice for you. You can practice with this problem, find the peak voltage, the frequency, in radians, and the frequency in hertz in the fundamental period from the diagram. Please keep in mind that when we draw diagrams like this, we need to show the units for the x-axis, for example, whether it is in millisecond, in second, or in another unit. For example, here I say time in seconds, and the y-axis, whether the voltage is in millivolt, microvolt, or volt, so we need to specify correctly. Okay, now these are the extra circuit symbols that we studied in the previous lecture. For a wire is like this, and for a resistor, the symbol is this: a capacitor, inductor, variable resistor, switch, lamp, and transistor. A transistor has three terminals here, 1, 2, 3. A diode has 2 terminals. This is a symbol for diode. And this is for battery. And for AC voltage, like this, voltmeter, ammeter, and for the ground, or for zero potential, is given by this. I hope you have an introduction about basic circuit elements and circuit analysis in these 2 lectures. For more understanding, please study the lecture notes posted in Blackboard, and also try to solve the problems in the examples by yourself. Of course, if you do not understand and if you have questions, you can always email me. Thank you for listening to this lecture, and see you in the next lecture.